So this lesson's or this video is going to cover buffers from the acids and bases section of the AQA specification, the A2 side of it, Chem 4, the Unit 4 part. So buffers. So it's not going to go into any details at this point. I'm assuming that you can calculate pH and all those sorts of bits. This is purely buffers. The starting point really is, well, what's a buffer? So a buffer is a solution that's used to keep pH constant. So particularly in biological scenarios, you might use it. So if you're using enzymes and things, you would perhaps have enzymes in a particular buffer solution to keep them at the pH that allows them to work and that stops them being denatured. So really, we're using buffers anywhere we want to keep the pH constant. Now, this isn't going to keep a pH constant forever. It's going to withstand small changes. So it will withstand small changes, or rather small additions of acid or alkali. So we are talking small additions, though. We can't be adding, litres and litres. If you've got a 50 centimetre cube buffer solution, if you add a litre of acid to it, you're going to break the buffer, and it's not going to keep that pH constant. We're talking small amounts, okay, that otherwise would change the pH quite drastically, but the buffer helps to reduce that. And you will get a small change, but it's so constant really here is, it's not going to keep it exactly constant, but it's going to keep it pretty constant. You're talking a second decimal point change often, with the addition of maybe 5 or 10 centimetres cubed of an acid or an alkali. So they're resistant to these small changes of H plus and OH minus and buffer. Now, a buffer itself is actually it's a mixture of a weak acid and its salt. And what I mean by that, so example could be ethanoic acid and sodium ethanoate. It's key that actually it's the acid and the salt that the acid would make, because that, when we start looking a second at the theory behind the buffers, that's very important because it allows for this the pH to be kept constant. If we had sodium methanoate, the whole thing wouldn't work quite so well. It needs to be the acid and its salt, but of course that could be propanoic acid and sodium propanoate, methanoic acid, sodium methanoate. It doesn't matter. It's just got to be the acid and its constituent salt, the salt that it can form. So the buffer itself then. So as I say, we've got this weak acid and we've got a salt. Now, of course, what we find is that two equations occur. So we have our sodium methanoate, for example. When we add that, when we have a solution, we'll start with ethanoic acid. So we have ethanoic acid in solution. It's a weak acid, as specified there, and as you should know. Therefore, it does not ionise completely, and that's the reason we have this equilibrium here. So weak acid, not complete ionisation. And over here we have the sodium methanoate, so the CH3COO Na. Now that does completely dissociate into the ethanoate ion and into the sodium ion. Now the sodium ion isn't really very important here. What's important really is this and this. What we have here then is when we add these two things together, we find that because of the way this equilibrium lies, and it lies very far to the left, we have almost, it barely ionises at all, to be honest. It's something like 4 out of every 1,000 ethanoic acid molecules will actually ionise. So it's very heavily weighted to the left-hand side. So we have lots of, and this is true no matter what the acid and what its salt is, but lots of CH3COH, lots of ethanoic acid, and we also have lots of the salt portion there, so lots of the ethanoate ion. So we have lots of the acid, lots of the ethanoate, and we have some H plus as well. Now this I should have specified really this. This is an acidic buffer. I do apologise, I haven't said that earlier on. This is an acidic buffer in particular. The basic buffer I'll come on to in a second. It's the same concept, but obviously with bases, not with acid. So I do apologise, I haven't said that earlier on. This is an acidic buffer. So that's obviously why we've got the some H plus there. So nice acidic buffer. Now, why, when you add acid or when you add alkali, why does the pH remain constant? Well, if we look at the idea of adding acid, so let's add acid, which of course, really we're talking about adding H+. Now, when we add the H+, what happens is the H+ will react with the ethanoate ions. So, reacts with the ethanoate ions. And in doing so, it produces ethanoic acid as a molecule. So the ethanoate reacts with the H+, producing ethanoic acid. And actually there, that's exactly what we want. We have removed the excess H+ by reacting with the salt to produce the ethanoic acid. Which, as I say, is perfect. It means that the pH will not change, the pH obviously being the minus log of the concentration of the hydrogen ions. Because the hydrogen ion concentration now has not really changed, because we've managed to mop up a majority of these, not all of these, but majority of them, that means that actually we're going to be in a position where we're not seeing a huge change in pH. Other way around, we'll say add alkali, and talking OH minus here. Now OH minus then, that's going to react with the H+. And you might think at this point, well, that's the problem, because if the pH is the minus log of the H+ ions, which is absolutely correct, if we're using these up, that's now an issue, because that's going to mean the pH is now going to increase. I've added the alkali, it's going to increase. But not so, because what happens is, we reacts with the H+, correct, but then this being an equilibrium, and this is the key thing, this is why the weak acid is absolutely imperative. We use this up, but the equilibrium now shifts to the right. So equilibrium, and I'm talking about this, obviously this equilibrium here, shifts right to replace H+. Now, again, it's not going to replace every single H+ there, but it's going to do a pretty good job, and we're going to see a relatively small change in pH. And we're talking pretty small. And that's the theory behind buffers, and that's actually very important, because when we come to look at the calculations in several minutes' time, this is very, very key. And actually, questions do come up regarding this. This could be classed as change the colour to make it stand out slightly more. Qualitative. So it's what happens when we add the acid or the alkali to the buffer without any numbers actually associated to it. It's a qualitative answer, so it's the theory behind the buffers. Let's flip it over to the other side then. Let's say, well, what happens if we were to use a basic buffer or an alkali buffer? So I'll call it, actually no, I'll call it an alkali buffer. Alkaline buffer. Now this time again we're looking for weak base, weak alkali. I'm going to use those terms interchangeably, it's pretty terrible, but there we go. Weak base, weak alkali, and it's salt again. So the example I'm going to use here is ammonia and ammonium chloride. And the similar idea happens. So the ammonia, we look at the dissociation of the ammonia. Well, again, because it's weak, it's a little bit more tricky in comparison to the acid one, which is very straightforward. But we have that occurring, and then the ammonium chloride, again, complete dissociation, complete ionization, again into the ammonium ion, and obviously the chloride ion. Now, we'll have a look at exactly the same as before. So what happens if we add acid? Well, we add acid, remembering that acid is obviously H+. Again, when we add the acid, it's going to react with the OH-, and exactly the similar. This is like the adding alkali. So when we add the opposite thing, if that makes sense, so we're adding acid to the alkali. When we add alkali to the acid, we have a similar idea occurring. It's involving the equilibrium. So it reacts with the OH-, which you might think, oh no, OH- going down, therefore that's going to affect the overall pH. Well, yes, but no, because of the equilibrium. So equilibrium shifts right to replace OH minus. Now at this point I feel like it's probably fair to say that actually I've never seen a question, as far as I'm aware, come up on the alkaline buffers, and certainly no calculations. The calculations all tend to look at the acidic buffers, and that's what I'm going to stick to in the questions in a minute, because I've used all past paper questions. But it's just an awareness. The same idea is true when you look at the alkaline buffers, but so just be aware of that. So we add the acid, equilibrium shifts to the right to replace the OH minus, exactly as in the last situation. So when we add the alkali, exactly the same as in the acidic buffer. It reacted with the salt portion. Well, it's going to do it this time as well. It's going to react with the ammonium, and therefore reduces the alkali being added, and therefore again pH remains constant. And again, this is a qualitative approach. It's the theory behind the buffers, but again it's important because it's important you can know what's happening so that the calculations actually make some sense. So that's the theory done. I'm going to move on to the calculations now. Before I start that, it's worth noting that actually these calculations are often worth a lot of marks, and they do take quite a bit of room, and you normally get almost a whole page for some of these questions of working, you know, the extra space, it's the entire A4 page. And the reason for that is that there are quite a few steps, but actually the steps aren't difficult, and they are, provided you know what you're doing and you understand this theory, those steps are really straightforward. And actually, you know, 6 marks for one part of a question, it'll perhaps take you 4 or 5 minutes, and that's, you know, that's a good number of marks to be getting. And actually, you know, people struggle with buffers, but they're easy marks to get hold of. So we'll start with an easy kind of question. In fact, we'll start with a question that actually relates to the theory, which is probably a fair point to start at. So the theory that we've just talked about then, explain why the pH of an acidic buffer solution remains almost constant despite the addition of a small amount of sodium hydroxide. So we go back up here, we go to our theory, which of course we've learnt by this point. Small addition of sodium hydroxide. Right, so the sodium hydroxide, the OH minus ions react with H plus. And then the equilibrium shifts to the right to replace the H plus lost. Boom, 2 easy marks. That's a fairly straightforward question. There is nothing there that you can't do. And again, that's just application. That's not even application. That's just recall of the buffer theory. Now, I'm going to rub that out. If you wanted that, then you'll have to go back and copy that down or whatever. And I'm going to go for the calculation type questions now, because these are what do trip people up. So the first one looks a little bit like this. Straightforward question on, this is probably the easiest kind of question you're going to get with relation to buffers, and that's just straight out calculate the pH of the buffer. And they're giving you various numbers here. So calculate the pH of the buffer. Now, buffer solutions, in terms of their calculations, it all factors itself around this, the weak acid association constant, or weak acid expression. So by this point, I'm assuming that you know this. If you don't, go back, sort it out. Ka is equal to Y minus concentration of the salt multiplied by H plus concentration of the H plus over concentration of the acid. And there we go, that's that. Now, at this point, there are a couple of assumptions you have to make with buffers. And if you don't make these assumptions, it's not going to go particularly well. And the assumptions are that, well, actually, let's rearrange this. We'll rearrange this first and then look at the assumptions. So we know we're going to work out the pH, therefore we're going to make the concentration of hydrogen ions the subject of the equation, because then ultimately we can do the minus log and we can get the answer. So turn that all round, flip it round, and we end up with Ka multiplied by Hy divided by Y minus. Now, this is where I'm going to go on to our assumptions. So the assumptions you make on these are that this concentration of Hy is equal to the concentration of the acid given to you in the question. We assume no dissociation of acid. So we can say this HY is exactly the same as this. We are assuming no dissociation has taken place, and we are also assuming that complete dissociation has taken place of the salt. So complete dissociation of the salt. Go over here. Let's put these numbers in then. So we are told a buffer solution was prepared by dissolving 0.0236 moles of the salt NaY in 50 centimeters cubed of a 0.428 mole per decimeter cube solution of the weak acid HY. So straight away, we're looking at these numbers here. I've got H plus, I've got my Ka value, so I know my Ka because it's given to me here. The Ka is 1.35 times 10 to the minus 5. I'm multiplying that by the concentration. Remember these square brackets equals concentration in moles per decimeter cubed. So all I can do is straight away put this in here. So 0.428. What I need to do though is I need to work out the concentration of my Y minus. Now you can do this either way. You could have worked out the moles of this from the information and kept this as the moles, or you can keep this as the concentration and change this to concentration. The reason you can't use, obviously, you can't use concentration here and moles here because they're different formats. We have to be dealing with the same things, and we either got to turn it to moles or turn it all to concentration. The reason you can change this back to moles is because the volume overall now, and we're talking about a solid here because it's a buffer solution was prepared by dissolving a solid salt into the acid. The overall volume is equal. So if you did the concentration, the volumes cancel. Concentration being the moles over the volumes cancel. Therefore, you can just use the moles. But in this case, we have to convert either, as I said, this to the moles from the values given, or convert this to the concentration. Now I'm going to convert this to the concentration, which is given. So I know that I have 0.236 moles, and I know that I have 50 centimeter volume. So I'm looking to work out my concentration. So concentration equals moles over volume. So 0.0236 divided by 50 times 10 to the minus 3. Obviously work that all out nice and carefully, brackets where you need to be, don't make any silly mistakes, and what you end up with is, once you've worked that through, you end up with something along the lines of 1.22 times 10 to the minus 5, and that of course then is our H plus concentration. Finally work out our pH. pH of course is minus log of the H plus concentration. What am I doing here? Right, pH now, which then if you calculate it out, you'll come out to 4.91. That's reasonably straightforward. This is probably one of the most straightforward questions you're going to get, in all honesty, in terms of pH. They could be a little bit easier. They could have given you rather than it being a solid, it could have been a volume there with a concentration. That would have made it a little bit easier, potentially depending on the overall volumes and working that out, making sure your concentrations are the same. But this is a reasonably straightforward question, and 4 marks there for actually what I don't think is too much hard work. 4.91. Do try and give your answer of pH to 2 decimal places always. Okay, that's a bit of a given really when we're dealing with pH. Stick to 2 decimal places. Often it will specify it in the question. And round appropriate. If that was 4.916, of course I would be 4.92. Okay, it wasn't. It was 4.91 something lower than 5. Therefore, 4.91 comes out as the correct number there, and obviously it gives me the full 4 marks. Lay out this well as well. If I was going to give you any advice, I would say make it clear the rearrangement of the equation. The only reason I say that is because if you make a mistake somewhere and you don't get the right answer, the examiner, you want to make it clear to the examiner that you have done every step, obviously. So make it clear. You know, I'd even perhaps do the Y minus step actually as a separate one. Then I'd substitute the number in, just so someone can really see what you're doing. And that way you're going to get marks. Even with the wrong answer, you could still pull up 3 marks on this, which is still pretty good, because people make calculator errors. They're stupid, but people do them. Okay, so we're going to go up here. There's the top. Move across. Couple more questions now. So next one looks a bit like this. Now this one is it's carry on from the last question. So it's the last one was 2D part 1. This is now 2D part 2. And now what we're saying is, well, we've got our buffer solution which we calculated in the previous part of this question. We're now adding some sodium hydroxide to it. How is that going to change the pH of this buffer solution? which is another 4 marks there for actually what isn't too hard. Now, we of course need our values from last time. Let's see if we can, and where are we? Let's go back down here, pick up these values. So it was 0.0236 moles, and it was 50 centimeters cubed of 0.428. And the acid, I'll just put that over here, 50 centimeters cubed, 0.428. Now, what you've got to imagine is exactly as we said previously when we talked about the theory behind these buffers, is when I add my sodium hydroxide, my buffer solution is going to undo that. And what it does is the sodium hydroxide reacts with H+, okay, to produce water, but the key thing is we are using up our H+. And to replace that H+, remember that this equilibrium exists. And so to increase the level of H+, which has now been decreased because of this reaction, I want to increase this so my equilibrium can shift to the right, which means I'm going to have to use up some of this. And that's the first step here, is that my acid, because of this effect here, my acid is going to go down. And that's a very, very important thing. And the way to do this is it's going to go down by the same number of moles as there are of hydroxide added. So we look at this, we know that 5 times 10 to the minus 4 moles of sodium hydroxide were added to this buffer solution, which means that 5 times 10 to the minus 4 moles of H+ will react. Now what we can assume here then is that they will be replaced by 5 times 10 to the minus 4 moles of this dissociating, which would obviously give me another 5 times 10 to the minus 4 moles of this. Note that it would also give me 5 times 10 to the minus 4 extra moles of this. Therefore, my salt will go up by 5 times 10 to the minus 4 moles. This is the moles of salt, I'll make that clear. Moles of my salt, which I think was Y minus, and the acid was HY. So that's going to go up by 5 times 10 to the minus 4. Go through that once more. I add the sodium hydroxide, which has a molar value of 5 times 10 to the minus 4. So it's 5 times 10 to the minus 4. That means it's going to react. So 5 times 10 to the minus 4 of this is going to react with 5 times 10 to the minus 4 of this. It's a 1-to-1 reaction. In order to replace this 5 times 10 to the minus 4, which has disappeared over here in this other reaction, this needs to dissociate, but that means 5 times 10 to the minus 4 of this must dissociate, meaning this goes down by 5 times 10 to the minus 4, but this goes up to leave us with an equal number of H+ in an ideal world. Therefore, our pH should remain fairly constant. But of course, it increases the moles of this, and that's the important thing. So that's why this has gone up by 5 times 10 to the minus 4. Now we need to work out our acid moles. We've got a volume, we've got a concentration. So moles is concentration times volume, so 0.428 times 50 times 10 to the minus 3. Remember to convert that to decimeters cubed, and we're going to take 5 times 10 to the minus 4 away from that. And we end up with two values. We end up with a value of 0.0209, and we end up with a value of 0.0241. So two different values there. Now, I'm going to have to quickly look back down here because I need to see what the acid dissociation constant was. 1.35 times 10 to the minus 5. So my Ka, 1.35 times 10 to the minus 5. Now what we do, that's the difficult step done. Now we just put our numbers back in. So I'm already going to, I'll write it out actually in full again. It's only good practice. So Y minus HY H plus. Rearrange. So H plus is the subject. It's going to be, what are we going to get here? Ka multiplied by HY divided by Y minus. Now what we can do here, we do not have to convert these back to concentrations. The reason being, as I said before, we have the same volume here and here, therefore that could cancel. So nice and easy, we just have to put our numbers in. So we put 1.35 times 10 to the minus 5. and we are then going to multiply that by our HY, so the acid, so 0.0209, the new value there, divided by our new value for the salt, 0.0241. We work that through and we get an answer of 1.171 times 10 to the minus 5. Another point here, do not round this. If you round this to 1.17 now, you're potentially going to bring in a rounding error early on. Only round at the end. Do not round midway through a calculation. So 1.171 ... What I would do, I'd use the memory function on your calculator and I would save that entire number. And I would then, in fact, actually, when you've got that answer there, all you've got to do is press the log button and then equals, and it will throw out your answer. So pH, of course, equals minus log of H plus. In fact, when I work out, when I go from H plus like this to pH, I don't even put the minus in, because if you just press log, it will give you a minus number, flip it round. So if you ignore the minus, you will then get, and you reverse the sign on the answer you get. That sounds confusing, but hopefully it makes sense. Or if you're not sure what I'm on about there, just put the minus in and it won't go wrong. But anyway, your answer here comes out at 4.93. Now if we compare those two answers, the previous one was 4.91, and you can see here we've added some alkali to our buffer, and it's done a pretty good job. The pH has increased by 0.02, which is a very small amount, a very, very small amount indeed, particularly when you think about what pH is, this logarithmic scale and all the rest. That's a very small amount indeed, so it's done a pretty good job. That's remaining pretty constant. I mean, in fact, you know, if you were just to think, if that was just to one significant figure, you wouldn't notice a change. In fact, you don't even notice a change to two significant figures or to one decimal place. It's only that second decimal place we've got to change there. So that's pretty good. And this is another question that they quite like to ask. And I've got one later on for you to try, which is where they're adding acid instead of the sodium hydroxide, but it's no more difficult really. Next question, and bigger marks for this next one. So a bigger question. There was actually more room here as well to write stuff on, and it's going to take up most of the page, this one. This is a slightly different way of making a buffer. So you can make a buffer by adding together the weak acid and its salt, so ethanoic acid and sodium ethanoate, potassium ethanoate, whatever. The other way you can do it is you can make it in situ if you like. You can take some weak acid and you can react it with some hydroxide, the ultimate thing being that you will produce some salt. So what I've got here is that there's a reaction. Starting point here is look at the reaction. So the ethanoic acid is going to react with the potassium hydroxide to produce me the salt and water. So an acid-base reaction. Now, notice here what I've got, and if I actually, well, I'll leave those there. Obviously, this is the OH minus ion. This will just be my salt here, which of course dissociates entirely. Now, this, you end up with a mixture of acid and its salt, which is exactly what a buffer is. You will not always, they won't always say calculate the pH of the buffer solution formed. It might just be calculate this pH of the solution when the weak acid is added to the hydroxide. Just be aware that it's still a buffer calculation. And the way you work this out is something like this. The starting point is to say, well, I'm going to work out my moles of acid, and I'm going to work out my moles of hydroxide. So moles of acid, moles of hydroxide. And I've got various values here. So my acid is this part here. So it's 25 centimeters cubed and 0.410 as the concentration. So moles, concentration times volume. So 0.410 times 25 times 10 to the minus 3. That will give us a value, which I'll stick up in a second. Hydroxide, same principle. Concentration 0.100 times 10 times 10 to the minus 3. So if we put these values in, what we find is that the moles of the acid are 0.01025, and the moles of the hydroxide added are 0.001. So we have two values here. Now, this involves a bit of kind of getting your head around this and a bit of thinking, but it's very, very logical. I've added some hydroxide ions, and I've added 0.001 moles. Originally I had 0.01025 moles of my acid. Now my acid is therefore in excess. that means that all of my acid cannot react because there's not enough of this to react with it. Therefore, this is the limiting factor as to how much of the acid can react. So 0.001 of this will react. Now that means all of this will react. My potassium hydroxide will completely react. All 0.001 moles will react. Now because this ratio is 1 to 1 to 1 to 1, if 0.001 moles of this react, they can only react with 0.001 moles of this. Therefore, my acid ends up being 0.01025 minus 0.001. Because we're talking about, basically, the buffer is formed after this reaction has taken place. And so the reaction is going to take away 0.001 moles of this in order to produce these two. Which means, and we can now actually ignore our hydroxide, but that means the moles of the salt, the CH3COO minus, I've just ignored the K there, is going to be equal to 0.001, as would the moles of the water, but we don't need to worry about the water. The key thing here is we now know the moles of this and we know the moles of this. And because the volume is equal, well, it's very easy. We just stick these moles into our Ka and straight away we're going to work out a value for the pH. So at this point now we have reached the bit where we can actually go and do some working. So, as usual, Ka is equal to, in this case, my CH3COO minus H plus over CH3COOH. Nice little line through there. Rearrange that so that H plus is going to be equal to Ka times the ethanoic acid divided by the salt, so the ethanoate ion, the concentration of. Work that out, we get an H plus value of 1.6095 times 10 to the minus 4. And all I've done there, I just skipped that, which was fairly bad of me. Ka value I'm taking up from up there, so it's 1.74 times 10 to the minus 5. I'm multiplying that by the value of the ethanoic acid, so this value that comes up here, which is 0.00925. Sorry I didn't do that earlier. So 0.00925, and I'm dividing that then by this value here, 0.001. And that gives me this answer here. And then the same thing as normal, pH is minus log of the hydrogen ions. Bish bash bosh, stick your numbers in and you find the pH is 3.79. By all means, work this through, do the calculations and all the rest, but you can see there 6 marks actually for a fairly straightforward standard way of working. And actually these questions all follow a similar pattern. You've just got to make sure that you don't make silly mistakes along the way. Your numbers are all clearly laid out. Hopefully you can see that what I've done here, it's really clear. I've made it obvious to the examiner and also to myself, and that's perhaps more important. I've worked out my moles of my acid initially, and therefore what I'm going to end up with afterwards. So you could even write here moles after. I've worked out my moles of the salt and my hydroxide, and I've then put it into the equation really clearly, laid it out nice and clearly. I've then explained what I'm doing at the end, pH, and then I've got my value there, 3.79. And that's it. That's 6 delightfully easy marks to get. Now I've got a few examples now, and what we'll do is I'm going to put up one by one. If you pause it and have a go at them, you can see how you get on. And yeah, just see how you go really with those. So first example. Right, so here's the first example. Have a go working through this now. See how you get on. So this is a fairly straightforward buffer, like the first one that I showed you the calculation. So all we're looking for here is simple use, really, the simple assumptions, and then a simple use of the expression of the acid dissociation constant. So going through then, if we write out our dissociation constant as the expression as it should be, so Ka equals HCOO minus H plus over HCOOH. Therefore, rearranging that, we're going to get H plus being equal to Ka multiplied by square brackets there, don't forget those, the HCOOH over the salt, HCO minus. And all we have to do then is just put our values in. So we've obviously, as always, given the acid dissociation constant, 1.78 times 10 to the minus 4. Multiply that by the concentration of the acid, which, looking at this, we're given molar values. Now we could convert those to concentrations, but obviously it's per decimeter cubed, so it would end up being the same. But again, there's no actual need to do that because we are given the total volume. So each of these would be calculated in the same way, and therefore the volume cancels. By all means, do that out, work it out fully, and if you don't understand what I mean, work it out fully, turning these to concentrations, you'll see where they cancel and where that cancel comes in. So 2.35 times 10 to the minus 2 over 1.84 times 10 to the minus 2. Put that into your calculator, making sure you get all the correct points, all the correct, indices there, the times 10 to the minus 4s and all the rest of it. And you should come out with a value something like 2.273-ish times 10 to the minus 4. As use the memory function in your calculator to use this value, do not round it. Finally, pH then is the minus log, as always, of the H plus ion concentration, and that comes out in this one to be 3.64. So that's probably one of the most simple buffer type questions you're going to get, in all honesty. They tend to then lead on into the further examples, as it does in the 2C part 2, which is up next. So again, it's one of these where we've added something to the buffer. This time we're adding some acid to our buffer that we had previously. Now remember what the numbers were previously, and I'll write these out first. Acid was initially 2.35 times 10 to the minus 2. Salt was initially 1.84 times 10 to minus 2. Work out the moles of hydrochloric acid first of all, which of course, remembering that the dissociation occurs like that, our mole of hydrochloric acid would equals 1 mole of H plus. Do bear in mind, as with ever, any of these calculations, if they're using sulfuric acid, obviously it's going to dissociate to 2H plus, and you've got to factor that in accordingly. That's a nice trick they love to play, but don't be fooled out by it, because it's not a difficult one to actually stay on top of, provided you've read the question. You know the sulfuric acid dissociates in that particular way. But anyway, this one is hydrochloric, so don't have to worry. Therefore, moles of hydrochloric acid is going to be equal to concentration times the volume, so 0.100 times 5 times 10 to the minus 3. We end up with a lovely value there of 0.0005. Now this time, hydrochloric acid, it's going to react in a slightly different way. And if we remember back to our buffers, and it should be here somewhere, we'll go up to our acidic buffer, which is, of course, an acidic buffer, as all of these have been actually. We're adding acid, so that's going to react with the salt, and that's a very, very important part. Let's see if I can find my question again. There we go. So it's reacting with the salt. That means the value of the salt is going to go down by this much. So that's going to go down this time, whereas before in the example similar to this, it went up, which of course means because this salt, the what was this? Ethanoic, I think it was ethanoic. No, it wasn't. It was the it was ethanoic ion. So the ethanoic ion reacts with the H plus to produce that. Remember. Now it is an equilibrium, but I'm going that way this time, which means I'm going to up this by 0.0005. So it's new values there, and my new values come out as, if we get this the way around, 0.024 and 0.0179. Stick it into your equation, Ka, I'm certainly not getting bored of writing this, CH3 COO minus H plus, you know the drill now, CH3 COOH. Rearrange therefore to find that H plus is equal to CH3 COOH times Ka divided by blah, 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 CH3 COO minus. Put your numbers in. It's going to be, oh dear, the acid dissociation from the previous question. Obviously in an exam you wouldn't have to cut and paste it like this, you'd have all the questions, but it was 1.78 times 10 to the minus 4. Go back if you forgot that, times the acid, which is 0.024 divided by 0.0179. We end up with a value of, skip the, no, actually no, I'll give you this value here, 2.3 386 times 10 to the minus 4. pH therefore equals 3.62. And again, you can see the previous one was 3.64. It's now 3.62. It's held on pretty well on that addition of the acid. Okay, final question. One of the more difficult ones now. One of the ones where we're making the salt in situ. Again, this was worth 6 marks. Have a go. See how you get on. Right, similar idea as before then. So we're reacting HX with this OH minus, which is going to ultimately produce this X minus and water. Work out moles of each. So work out the moles of HX, work out the moles of OH minus. That's what I mean by N here, moles. So the moles of HX are going to be equal to, where are we here? So this is our acid part here. So 15 centimeters cubed, so 0.174 times 15 times 10 to the minus 3. Gives us an answer of something. Hydroxide is going to be 0.125 times 10 times 10 to the minus 3. A couple of answers there. We're going to find for the hydroxide, the number of moles there are going to be 0.00125. Up here, the moles are going to be 0.00261. Again, this is in excess, which we would hope. Because this is in excess, all of this will react, and therefore moles after are going to be 0.00261 minus 0.00125, which is going to, of course, equal 0.00136. That means, so that's moles of HX after. Moles of the, what's it going to be? X minus there, which is going to be the salt. That's going to be equal to this value of the hydroxide, so 0.00125. As per the exact same reason as before. Okay, I'm whizzing through this so it doesn't end up going on too long. Put your values into the equation one last time, thankfully. Ka equals try and get my head now. That's sudden blank. There we go. X minus H plus HX. Rearrange that to find that H plus is equal to HX times Ka divided by X minus. Stick our numbers in from here, so we know that HX, well, we know first of all our Ka 3.01 times 10 to the minus 5 multiplied by acid, that's this one here, 0.00136. Not worrying about volumes again because the volume is the same, therefore it's going to cancel. And X minus is going to be 0.00125. When I say the volumes are the same, I mean the overall volume once reaction has taken place is going to be the same. Obviously, initial volumes are different, but we don't have to worry about that. 0.00125. Work that through. We get an answer of 3.27 blah 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 times 10 to the minus 5. Squeeze it on there, and finally pH equals 4.48. 2 decimal places like it's specified. Temperature here makes no difference. It's just they're putting a temperature in there. It doesn't matter. We don't need it. That's buffers with some examples. Hopefully that has been of some help. Hopefully, as I say, that that has helped a little bit. You now have a better understanding of buffers. Any comments or anything, please do leave below. And there you go. That's buffers for you.